Hello, welcome to the next video in the AD400 lecture series. We're going to talk about software quality assurance today. And this is a direct follow-up to the quality concepts video that I did previously. So the first thing we're going to talk about is this guy, Phil Crosby, and he said, the problem of quality management is not what people don't know about it, it's about what they think they know about it. So here's some expansions on that. Everybody's for quality management. I don't know anybody who's like, hey, I would prefer this to be poor quality, right? Everyone wants it to be good quality. Everyone kind of gets the feeling like they understand it, even though nobody's going to really stand up and say, hey, I'm going to also explain it. But people say, oh, yeah, I know what quality software looks like. And, this kind of relates back to that philosophical view of, I think it was transcendental quality, where, quality can't really be defined, but you know it when you see it, right? So people think, oh, yeah, I know it when I see it, but I don't really want to tell you what it is. Everyone thinks execution is only a matter of following natural inclinations. After all, we all do get along somehow, so people believe, oh, if what I believe it should be, yeah, if I follow my natural inclinations, it'll be quality. And most people feel that problems in these areas are caused by other people, and if only they would take the time to do things right, it would be quality. And in reality, it's probably caused by a collection of people, not only a certain number of people. So assumptions can be a real problem here. Assuming that you know what quality is different from taking the time to actually learn and produce quality. All right, so there's some aspects here to software quality assurance. We want to define our process, have a method involved with change control, have reviews and testing, establish methods and tools, have audits and compliance, and then measurements and reporting. So all of these together develop a robust quality SQA, or software quality assurance. Okay, here's some elements of SQA. So we have standards. Our IEEE, ISO, and other standards organizations have produced a broad array of software engineering standards and related documents. They're adopted voluntarily by software engineering organizations, or they could be imposed to the customer by stakeholders. So the job of SQA is to ensure the standards have been adopted and they conform to them. Reviews and audits are technical reviews. These are like code reviews that are done by software engineers. And the idea is we want to uncover errors. Audits are actually a type of review performed by SQA personnel with the intent of ensuring quality guidelines are being followed for software engineering work. For example, an audit of the review process might be conducted to ensure the reviews are being performed in a manner that leads to the highest likelihood of uncovering errors. Testing, software testing is, what we're going to really dive into next quarter. This is the actual on-the-ground implementation of quality control, where our primary goal is to find bugs or errors. And so testing needs to be planned properly and has to be done in multiple ways in order to ensure that it achieves its primary goal. Error defect collection and analysis is the only way to improve is to measure what you're doing. So SQA collects and analyzes error and defect data to understand how the errors were introduced and what software engineering activities are best suited to eliminating them. Change management, we've talked about there. Change can be one of the most destructive aspects to a software project. If it's not managed properly, it can lead to massive amounts of poor quality. So that needs to be established. Software quality assurance makes sure change management processes are established and efficient. Education, we want to make sure our software engineers are educated. A big factor to improvement is ensuring that the software engineers and the managers and the stakeholders are educated. And whatever we're educating them on, whether it's the domain or on actual software development. So vendor management is going to be 3 categories of software that are acquired from external software vendors. We have shrink-wrapped packages, a tailored shell, which provides a basic skeletal structure that is custom tailored to the needs of the purchaser. Shrink-wrap package, by the way, would be something like Microsoft Office. It's all ready to go. And then contracted software that is custom designed and constructed from specifications provided by the customer's organization. The job of the SQA organization is to ensure that high-quality software results by suggesting specific quality practices that the vendor should follow. So this is a form of communication between the vendor and the SQA organization to ensure that they are also following processes that ensure this quality is going to happen. Security management. Obviously, if you're going to have secure software, you're going to have quality software. We need to protect the data at all levels, ensure firewall protection for all types of apps, including mobile apps, and make sure the software hasn't been tampered with. Safety. Safety is going to be always a pivotal component of software development. We need to look for any sort of defects that could be catastrophic. SQA will be responsible for assessing the impact of software failure and initiating those steps to reduce risk. And finally, risk management, which we have talked about in this class, is going to be the mitigation of risk through proactive measures. Okay, so I'm a big fan of data and the way data plays a role. So we want here to ensure that our data, our SQA, is data-driven. So we identify a problem area, identify indicators that are showing that there's a problem, prepare criteria for any sort of quality that achieving the quality where the defects are or the problems taken care of, and we compare the results of implementation, analyze the assessment, and take measures to improve, and then it just keeps happening again. So you identify a new problem area, identify indicators, or maybe the same problem area if it was not completed, but you continue following this cycle. All right, so the role of a software quality assurance group is that they need to develop a software quality assurance plan. It's going to identify the evaluations to be performed, audits, reviews, standards that are applicable to the project, any procedures for error reporting or tracking documents to be produced, and the amount of feedback we want to get back to the software project team. So the SQA group is also going to be participating in the development of the project software project description. And this is basically reviewing the process description, ensuring that compliance is happening, that standards are being maintained. They're going to be reviewing software engineering activities to be looking for compliance in documents, tracking any deviation or corrections that have been made. They will be developing audits that will be auditing designated software products, verifying the compliance is happening as well, looking at documents again, tracking deviations, things of that nature, and ensuring that deviations in the work and work products are documented, well handled. So a lot of this SQA work is a lot of documentation. And why we need a lot of documentation here is because we need some sort of formalization of evidence or verification that there is been processes in place to ensure this quality exists. There needs to be checklists to ensure that the quality exists. There needs to be step-by-step procedure to get to that final portion where we can say that, it's passed all the quality checks. Some of these companies are making software for mission-critical applications, as we've talked about before, and it could be a make or break situation, right? If you produce a poor quality piece of software and it's being used for something like 911 calls or, the fire department or something, you could be facing litigation and legal problems if your software is not of high quality. Even if you don't have some mission critical application, you're giving this product to people who are going to be using it to make money. And anytime a company loses money because of a product sold to them, I promise you, there's going to be some sort of retribution. So you need to keep these things in mind. This is no joke. Another fantastic reason why people like us get paid more than other people is because we are really creating products that are going to be making or shaping the way other companies are going to develop or possibly not develop. Okay, so some of the goals of software quality assurance. We need requirements quality, so the correctness, completeness, and consistency of the requirements model is crucial for the success of the project. SQA aims to ensure that the requirements are well-defined, unambiguous, and accurately reflect the needs and expectations of our stakeholders. We do requirements reviews, inspections, validations, helps identify and address any issues or inconsistencies in the requirements, and in turn improves the quality of all subsequent work products. We have to worry about design quality. We focus on assessing the quality of the design model. They were going to make sure the design meets specified requirements, exhibits high quality in terms of structure, organization, modularity, and adherence to architectural principles. It also reviews the design artifacts and to identify any design flaws, inconsistencies, or deviations from the requirements. Code quality is also a big deal. We want to ensure that the source code and related work products are of high quality. We're going to be doing this by measuring the consistency and readability of the code, having code inspections, code reviews, correcting coding errors, inefficiencies, and violations, and ensuring code best practices are followed. This leads to better maintainability, readability, and understanding of the code base. Also, documentation around what's being done in the code so that those who come later can actually understand what's being done and ensure that quality persists. Finally, quality control effectiveness. SQA is going to play a vital role in optimizing the effectiveness of the quality control activities. It focuses on allocating limited resources such as time, budget, and personnel in a way that maximizes the likelihood of achieving a high quality result. It ensures that the quality control processes such as testing, inspections, and reviews are properly planned, executed, and monitored. All right, so here's some examples. Here we have a goal of requirement quality and some attributes that we would be looking at, such as ambiguity. How many numbers of ambiguous modifiers do we have? Completeness, the number of TBAs or TBDs, TBAs to be announced or TBDs to be determined. Understandability, which is the number of sections or subsections. Volatility, I'm not going to go through each one of these, but you can take a look and you can see what these are. Design quality is another goal. We can look at architectural integrity, component completeness. We've talked about some of these before. Interface complexity, patterns. Want to look at the patterns that are being used, design patterns. Code quality, we're looking at complexity, maintainability in our design factors. Can it be maintained? Understandability, right? Is it understandable? Do we have reasonable variable name conventions, percentage of our reused components? Reusability, how much of it's being used? Again, it's kind of following the same thing. Our readability index for our documentation. And then with our quality control effectiveness, we want to make sure that things like resource allocation, staff hour percentage per activity is good. We're actually budgeting completion time versus actual time. Our reviews are effective and our testing is effective and is helping to improve the quality of the product. Formal SQA is going to assume that there's a rigorous syntax and semantics that can be defined for programming language, something that we can measure against to test for quality. We also want a rigorous approach for the specification of our software requirements. and I feel like I'm beating a dead horse here, but the idea of like ensuring that our requirements are done in a way that there's no redundancy, that there is not going to be overlap or conflicts. We can apply mathematical proofs to our correctness techniques to demonstrate that it conforms to our specifications. And so a lot of, one of the things that I've said before, and this is true, a lot of commercial developers are rarely performing these formal methods, but they can definitely be very helpful. Okay, what is statistical software quality SQA? So first, we have information about software errors and defects is collected and organized. And then an attempt is made to trace each error and defect to its underlying cause. So example, a design error, violation of standards, nonconformity to specifications. And then we can use something called the Pareto principle, which is 80% of the defects can be traced to 20% of possible causes. If we can isolate the 20%, we call that the vital few, and we can find out what's going on. And then once the vital few causes have been identified, we move on to correct the problems that cause the errors and defects. All right, so I'm not sure if you've ever heard of Six Sigma before. Six Sigma is derived from 6 standard deviations from the mean. So 3.4 instances or defects per million occurrences. It's an extremely high quality standard. The 3 core steps that go with Six Sigma is we define customer requirements, deliverables, and project goals through well-defined methods. We measure the existing process and its output to determine if it's got quality performance. And then we analyze our metrics and determine what the vital few causes are, what we just talked about before. Right? So this process is followed, which can lead to this level of quality. And there's a whole ton of information about how to follow Six Sigma processes and achieve that for software engineering. If we have one that needs improvement, we want to improve by eliminating the root cause of the defects and control the process to ensure it doesn't happen again. For any new process being developed, we want to design the process to avoid root cause of defects and meet the customer's requirements, and then verify that the process model will in fact avoid those defects and also meet the customer's requirements. So this can be a little tricky sometimes, ensuring that you are able to accomplish both of these. There is a simple measure for reliability, and it's called the mean time between failure, MTBF. It is the sum of the mean time to failure and the mean time to repair. So the mean time to failure represents the average time duration between consecutive failures of a system or component. It measures the reliability of a system in terms of how long it can operate without experiencing a failure. It's usually calculated based on historical data or reliability testing. So for example, if you had a particular computer component with an MTTF of 50,000 hours, it means on average, this component is expected to operate for approximately 50,000 hours before it fails. A higher value indicates greater reliability, as the component is less likely to fail in the given time frame. Mean time to repair represents the average time it takes to repair or restore a failed system to its normal operating condition after a failure has occurred. So to calculate this, you would need to consider the total downtime due to multiple failures and divide it by the number of repair incidents. This can be influenced by various factors such as the complexity of the system, availability of spare parts, if you're having any hardware portions, and the skills of the maintenance personnel. So for instance, if your system has an MTTR of 4 hours, it means that on average, it takes about 4 hours to repair the system and bring it back to normal functioning when this occurs. So you can see this all gives us the ability to measure software availability, which is the probability that the program is going to be operating according to the requirements at any given point. And we use this equation to determine that number. Okay. So let's talk about AI and some reliability models. Here, software reliability is referring to the probability that a software system operating without failure over a specific period of time in a specific environment. It's a key quality attribute that measures the system's ability to function correctly and consistently under various conditions. It's often assessed through testing, monitoring, and analysis of historical data to determine the likelihood of the failures occurring in the production. By improving this, we can have developers aim to enhance customer satisfaction. Bayesian inference, and we learned a little bit about Bayesian processes with your Bayes theorem, is a statistical method to update the probability of a hypothesis being correct as new evidence or information becomes available. So in software reliability, this inference can be applied to estimate the reliability of a system based on the observed failures and other relevant data. As more data about the performance, usage, and failure dates is collected, this allows us to continuously refine this and do more reliable predictions. Predictive data analytics uses things such as regression models involving MTBF, which is our mean time between failures, to help identify patterns and correlations between failures and specific software components and conditions. This allows us to be proactive in addressing potential vulnerabilities and focusing efforts on critical areas. And finally, we have these genetic algorithms, which are a class of optimization algorithms inspired by the process of natural selection. So in the context of software reliability, they can be utilized to grow reliability models by discovering relationships using historic system data. By analyzing past software component failures and their associated factors, we can identify patterns, dependencies, and contributing factors that impact system reliability. Software safety, I've talked about before, is a big deal. It's about identification and assessment of potential hazards that are going to negatively impact the software and cause the entire system to fail, which would be pretty devastating. So if hazards can be identified early in the software process, we can avoid them. So the ISO 9001:2015 standard is the quality assurance standard that applies to software engineering. And you can see the topics that it covers here. A lot of these things we've already talked about. So for an organization to become registered under this, it has to have procedures to address each one of these requirements listed. All right, so finally, we're going to take a look at some SQA plan contents. Through these, you can create a SQA plan for ensuring that you have quality assurance in your software. So the plan begins by stating its purpose, and it seeks to establish a framework for implementing and managing SQA activities through the software development lifecycle. It develops the scope of the plan, outlining which projects, phases, or specific work products are covered. The description of the software engineering work products, it means that it's going to have a comprehensive description of all the software engineering work products that are going to fall under the purview of the SQA. This is going to be requirement documents, design artifacts, source code, test plans, test cases, any other deliverables that require quality assurance. Applicable standards and practices. Our plan specifies these standards, and it is applied during the software development process. These are going to be like your industry-specific standards, either from ISO or IEEE, organizational standards, coding standards, design principles, any sort of testing methodologies. SQA actions and tasks are going to be like your reviews and your audits. These are going to be done through the entire software process. The plan will describe how it's done, how it's performed, and that it will be very detailed and very specific, because these audits and these software code reviews are going to allow for quantitative data to be developed to show evidence that the quality is being met. Tools and methods that support SQA and activities. We want to have automated testing, code analysis tools, version control systems, defect tracking systems, any other software tool that allows us to ensure quality. So the plan would explain how these tools are integrated and the development process. Our software configuration management procedures are going to be describing the process for managing software configurations, such as Gradle or whatever tools are being used. It'll also include version control, baselining, which we talked about before, how change control will happen, what's going to happen in release management, how are our software artifacts documented, tracked, and controlled. And that allows us to maintain consistency and integrity. We want to safeguard and maintain SQA records. So how are we going to ensure that they are maintained and their integrity is maintained? Guidelines around documentation management, record retention, and access control. These things come in handy, guys, when your company may be facing some sort of litigation procedure because of the quality of your product, and you may lose a lot. If you have all these records, you give them to your lawyer and you're in better shape. And finally, organizational roles and responsibilities. So this defines the roles and responsibilities of all the individuals and teams involved: project managers, developers, testers, other stakeholders. It clarifies also who is accountable for specific SQA tasks and ensures everyone understands their responsibilities for achieving these quality objectives. So in the end, it's who to blame. All right, well, thank you for sticking with me through this video, and that should be it for these videos. So thank you.